Welcome to this third APL quest. See the APL wiki for details. Today's quest is the third problem from the 2013 round of the APL problem solving competition. What is in a word? The task is to write a defin which returns the number of words in a given text, which can be given either as a single character or as a vector of characters. What defines a word for this problem is space delimited, but there could be multiple spaces between words. That can be leading and trailing spaces in the input. We have to account for that. Let's begin by creating some test data. So this is a normal text, but I put in a dash here so that we make sure that we're splitting on the right thing. This is a single letter, and we can also have an empty input, and then we have a text with more spaces, so we can have some leading spaces and maybe some trailing spaces as well. Okay, let's get started. Maybe the most obvious approach is to split on sequences of spaces, and we can do that by, let's say, if we start by comparing an input string with a space, and this gives us a Boolean vector indicating where the spaces are. Now the partition function groups runs of ones, or elements corresponding to runs of ones. So we want to invert this, and then we can use this to split. So we use partition on the string itself, and that gives us the individual words, and we can count them. If we try to do that on a string that has more spaces, we can see that it still works. 4 words there, and that's because any run of zeros is an area that gets cut out, and we split up at that point. Now this runs into a problem if we try to do it on a single letter, and that's because we cannot partition when there are no axes to partition along, so we must ravel first, and then it works. It also works on the empty one. That's not a problem. So we can put this together to a fairly straightforward tacit function. We want the tally of where the spaces are different from the argument, partition enclose the ravel of the argument. So we are binding the space to is different from function to achieve a monadic function there. If you come from other programming language background, and especially Perl, you might grab for regular expressions for this. So we can try that approach as well. We have our string, and then we have the quad-S, that's a string search, regular expression search, and the pattern we want here are with the inverted character class, none spaces, any number of those, one or more, and then it doesn't really matter what we're going to return because we just want to count them. We don't actually want them. So the best option here is use code 3, which means the pattern num in the offset from the left, and that since there's only one pattern, that's just 0. So we get a bunch of zeros. Then we can see we get 1 0 per word there, and that works also on the scalar letter, and it works also on the empty. We just get nothing, and then we just need to count them. As we can see here. So that's our second solution. Right there. Okay, here's an interesting solution that I came up with. It's kind of abusing a built-in functionality, a system function called VFI, that's verify and fix input. And really what it does is it parses numbers. So we can see if we give it some text, then it looks at this input as a space separated field. We can also have multiple spaces, and that's fine. It removes all such extraneous spaces, and it returns a 2-element vector. The first element is the success, and it says 1E3, that successfully was converted, and the word 3 was not successfully converted. 2.5 was, and 2.5 was not successfully converted. And then the second vector are the values that we converted to, and with zeros for those tokens that could not be converted correctly. Now we're not interested in what the actual values are, we just want to count how many such space separated tokens there were, whether or not they could be converted successfully or not. So we get the first vector, which is this Boolean, and then we can just count the number of elements there, and that gives us 4 tokens. So this works for all our inputs, even for the empty one, and it works for the single letter as well. It just treats it as a text. It's one with more spaces and our original string. So that's an additional solution. In order for this to be a proper function that we can give a name, then we need to bind together, or compose together 2 functions. So for example, the first 2. We can also compose the second 2. It doesn't really matter. Right. So far for these approaches where we're actually parsing and splitting up into tokens, but there are better ways to do this in APL. But for that we have to work with Boolean masks. And the way we often do it in APL, we compare a scalar with a vector. So here is our string, and then we have bits for each one. Now we're not going to use this to split up, rather we're going to analyze it. We want to know how many words there are. And what defines a word is that we have a separator, and there could be multiple separators. Let's try it with M. And then we have something that's not a separator. So we're looking for this pattern here, where we're going from spaces to non-spaces, and again here from spaces to non-spaces, from spaces, there could be many spaces, to non-spaces. And that's what gives us a count of words. That's one way to do it. And the way we can do this is by comparing adjacent elements. So we do the n-wise reduction. So here it's a 2-wise reduction on this. And so this means we're taking every pair of 2 overlapping windows of 2 and comparing them to each other with less than. Why less than? Because in a Boolean vector, we can use less than as a Boolean function to find out it only becomes true when we have a 0 on the left and a 1 on the right. Right? 1 is not less than 1, and 0 is not less than 0, and 1 is not less than 0. So that's the only time when it will match. And we can see here if it gets 1 element shorter because we're doing pairs. If we line them up, we can see how this 1 corresponds to this 0, 1 here. Or every time we have a 1, we begin a word. So this is fine. Then we can sum this, and that gives us a number of words 4. However, there's a problem. If we look at our string again, where it doesn't begin with any spaces, then let's go back and see what happens here. We compare this space, and so far so good, but now when we do the pairwise less than, then we're missing 1 element at the beginning, because sure enough there is as non-space at the beginning of the string, but we never go from 0 to 1 because there's no zeros there. So we're missing a 1 at the front. So how can we fix this? We can insert a space. So by inserting one space, it doesn't matter if we have multiple spaces, because we know from space to space, is just 0, 0, and that doesn't trigger. But this will insert a 1 at the beginning. You can see if we go back to the one that already has spaces, then it doesn't add any additional 1s. So this gives us the solution, and we can sum it like this. It gives us the number of words, and we can just wrap this in braces, and then we have our solution. Oops. And this is a pretty good solution. If you want to optimize for performance even more than this, then we have to think about how the data is represented in memory. Now, as we come into our function, then we have this name, the variable name omega, referring to the whole argument, and it may occur later again in the function, and therefore the interpreter has to keep this value available at all times. When we concatenate a space at the beginning, we'll need to make a new copy of this, and so this, if it's a very large argument, then we're going to spend a lot of time writing to memory just a copy of everything with a space in front. There are things we can do about this. Notice that here the data type is whatever type of character array it is. So normally it's 1 byte per character, but if we have some Unicode things in there, you can end up with 2 bytes or 4 bytes per character as internal representation. It can be rather expensive to write the whole thing again. Once we've done the comparison, then we are down to Booleans. So that's only 1 bit per character, because it's in the comparison. And since we're adding a space in the beginning, and space is not different from space, so we know that we're going to begin with a 0. And that means we can put in a 0 here and avoid copying the whole array. And that's going to give us somewhat better performance. But there is even more we can do, because if you think about what's happening, again, we have a Boolean array here, and we have to rewrite that but when we insert a 0 at the front. Because in memory, we have a header that introduces the array, and then we have the data from the array. And if you want to insert an element at the beginning, then every element, every bit has to move over 1 step, and we have to rewrite that whole array. We can do that in place, but it's still a rewrite. So if we can get rid of that inserting something at the beginning, that will give us a performance benefit. Now, how can we do that? Well, if we think about it, the only reason we want to insert a bit at the beginning is because we need to make sure to get the right result when we don't have any leading spaces. In other words, if we're missing a leading space, that means we're beginning with a word that's not being counted. And that means this mask, this Boolean array, the first element indicates whether or not we're beginning with a word. So we can just add that value to our total count. So we take the first element of the mask and add that to the sum, and then we just have to save the mask value right there, give it a name. Here's another problem, which is if we have a one element vector or scalar here, then we can't do the pairwise thing correctly. So, well, actually we can do it if we have a one element vector. If you have a scalar, we can't do it correctly, because so we have to ravel that as well. But there's actually a simpler way to do it, and that is simply inserting value on the right. Now, if we think about it, we're doing pairs, and we're doing with less than. And what we want to do is detect the words. We're going from spaces to non-spaces. But instead, if we detect the end of the words, meaning going from non-spaces to spaces, then we only need to append rather than prepend a single value. And appending something to an array, that is often very cheap, because we don't need to move all the elements of the array. Rather, we can just extend it by a little bit. The interpreter by default will allocate additional memory at the end of the array. And if you're talking a Boolean array like this, that additional bit might even be inside a single byte that has already been allocated, making it even cheaper to do. So how can we formulate this? Well, we can't just put a 0 at the end. If we go back to this solution here, because what we want to trigger is another. Now we're not worried about a word beginning at this right at the beginning of the string. We're worried about words ending at the end of the string, and we need to have another triggering of a word ending. So word endings are indicated by the pairwise less than, and we only get those if we only get an indication if we have a 0 on the left and a 1 on the right. And also now, since we're interested in where the spaces are at the end of the words, then we need to flip this around to an equality. So let's actually try this. So we have our string here. Let's print it out again so we can see. So now we are trying to find these places where a word ends. So we go from a 0 to a 1, and the problem is at the end there's no space there. So what we can do is we can go and, instead of doing a normal concatenation, we're doing a flipped or commuted concatenation. And this shows us the word endings even for when the string ends with a word character. And now we can do the comparison as before. And we can sum that to get the word count. We can try that with additional spaces as well. It works as well. Let's look at what's happening here. So M is this one, and there are additional spaces at the end. And then we compare to spaces. And we can see there's an extra space there at the end. But it doesn't matter when we then concatenate another 1 to the end, because the only thing that we find is when 0 goes to 1. So it all works as it's supposed to, and then we sum it and we get our result. We could also have done the opposite. We could have kept the inequality and appended a 0 and flipped the direction of the comparison. So it would be greater than instead of less than. It would be exactly the same. And let's give this a name. We'll put the argument name here. And let's look at all our definitions that we have. And at this point, we're going to have a look at what the performance looks like. And I could predict this already. Splitting up into substrings is going to be expensive. We're going to have lots of pointers, one for each word. And spinning up a regex engine is going to be expensive as well. And the same thing with quad-VFI is going to be expensive, because we're actually trying to parse every single token, whereas we only really need to look at where those tokens are to count how many there are. So it's absolutely certain that the last 4 solutions are going to blow the first 3 right out of the water. Let's see how badly. So let's create a text here, for testing purposes, and we can see we're going to let's just try it first to see what it looks like here. We reshape 4 into 20 elements and then random elements. So we're going to create some random text here. You can see what that looks like. So that looks kind of like a natural text. We don't care about what the characters are. Okay, let's make it big then. So here are 1,000,000 of characters. Let's copy CMPX in from the defense workspace. And then we can start off here with F on T, G on T, H on T, and let's just take I, which is the least efficient going to be of these, and to see what that looks like together. Give it a moment to compute. And we can see indeed that the Boolean mask-based solution is not even measurable in speed compared to the others. But it's interesting, the most expensive one was spinning up the regex engine to do this. Quad-VFI had to do a lot of work as well in identifying the tokens. Splitting into substrings was then the fastest among these. Now let's compare the 4 Boolean solutions to see if what we're expecting is actually holds true. So this is I, J, K, and L. And we'll see that our expectations held up. The solution where we prepended a space and therefore had to copy the entire array consisting of 1 byte per character and was the slowest one. When we changed to prepending a bit to a Boolean array, that gave us a significant speed up. It took about half this amount of time. But avoiding the copying of the array, either by saving the mask and looking at the first bit of it, or by appending a bit rather than prepending a bit, gave us the most significant savings. Thank you for watching, and see you next week.